quantum field theory, historical perspectives. I think Doug gave a better presentation on this than what I have here. So this is just sort of a review. It originated as the problem of black body radiation near the end of the 19th century, beginning of the 20th century. And there was something called the ultraviolet catastrophe at small wavelengths. And so that was sort of what was impelling this. And here is Planck's second paper, and it has this term on the right, the 1/2 h bar omega, which is the 0-point radiation energy. And it's called 0 point. It's actually temperature independent because it doesn't just occur at the 0 point. For cavity dimensions between 100 and 1,000 nanometers, which is sort of near ultraviolet to near infrared, you have the Casimir effect, and it can take place at room temperature. All right. More historical. Walter Nernst, who's a physical chemist best known for the third law of thermodynamics, writes a paper showing the vacuum of space also possesses fluctuations. And 1927, you have Heisenberg, the uncertainty principle, and that's what's believed to be behind these fluctuations of matter and space. Back in 1948, Casimir wrote 2 papers. The first paper with Dirk Polder explains the effect as an extension of the van der Waals forces. And the equation here is an energy equation for these 2 electrostatically polarizable or magnetic polarizable atoms. And the Casimir-Polder forces result from energy that's internal to the plates. You can see some atoms there, I, J, and K, in plate B and plate A. And so there is an energy difference or an energy between the atom in one plate and the atom in another plate. And if you were to add up all of these pairs, you would have the total energy, and from that you could figure out the force. And the question I ask at the bottom, can they be anything other than conservative? And interestingly, the Casimir force are known to be non-additive for many cavity geometries. But this whole, I'll get into this whole thing of conservative and non-conservative a little bit later. All right, what happened here? Oh, okay. And Casimir's second paper, also in 1948, is based upon the 0-point energy as suggested by Niels Bohr on the attraction, and the paper was on the attraction between two perfectly conducting plates. And it yields this familiar parallel plates formula. And the perfectly conducting plates, it's based upon the boundaries consisting of perfectly conducting uncharged plates. And so the voltage and is 0 on the plates. It gets grounded. And so the only whole number of half wavelengths can be within the plates. But there's no such restriction outside the cavity. And so there's more energy outside the cavity than in. So the plates are pushed together, resulting in the Casimir effect. But many believe that the two formulations of the Casimir effect are equivalent. And if that's the case, since the Casimir-Polder formulation essentially has to be conservative, that would mean that this would have to be conservative as well. And it's a bit of an issue with me since, well, you'll see why as time goes on here. Experiments. An early experiment was performed by Marcus Barnay with parallel plates in 1958. It was only partially successful, had large experimental errors. The first direct measurement of Casimir forces was by Limereau in 1997. And the first measure of lateral Casimir forces is recorded in a paper by Chen, Mohedin, and Klimchatkaya and Mostopenenko in demonstrations of the lateral Casimir force. This paper was sort of an inspiration for me. So it's I'll go into it just a little bit. This is sort of a diagram of an atomic force microscope. And he had a ball that's metallic, and it has sinusoidal corrugations on it. And he's got a flat plate, which is also corrugated with these sinusoidal corrugations. And he's moving the cantilever, or actually, it's the flat plate that's moving towards the cantilever. The cantilever is fixed. And you can see there's a laser here and a photodiode. And that's a way of taking measurements off of this. But they measured lateral forces. But the experiment was not designed to measure external forces. So this takes us to perfectly conducting wedges. And there are a number of papers here. The first one being in 1979 by Deutsch and Candelas. But there have been a whole bunch on the perfectly conducting wedge. And so here's a diagram of a perfectly conducting wedge. And all of these papers give this formula here. And the force, which is a force, is a force per area, which essentially is a pressure. Let's see, is determined by the angle alpha and the distance from the apex or the vertex. And so you can see there are two forces in red that are perpendicular to the plate. And if you decompose these forces, you'll get two forces that are equal and opposite and cancel out. And there are two forces that add up in the direction of the wedge bisector. And there's no reaction force here. So could it be a source of energy? This here shows the relationship to parallel plates. And by a simple transformation here, you find out you get the parallel plates formula again. All right. If you were to do this with have the parallel plates filled with media, it turns out it's the same wedge formula, but divided by n, which is the index of refraction. So, what are our experimental objectives? First of all, want to observe external forces at the microscopic level, want to observe external forces at the macroscopic level, and determine if these forces are useful for propulsion, which may be the same as determining if the forces are conservative or non-conservative. All right, so my a colleague in Germany, Dr. Thorsten Ludwig, did an atomic force microscope experiment for me. And it looks, without, getting into detail, somewhat similar to the Mohideen experiment, but actually it's a lot different. We have different grooves here. We have sawtooth grooves, and only one half of the groove is metallized. The plate, the fixed plate, is metallized. So there is a sense a wedge formed, and you need to do the cantilever ball thing twice, because you need to do the wedge in the opposite direction. So in the top one here, there is a force pointing up, and so the lateral force would cause the cantilever to bend up. And in the bottom one, it's the opposite. The cantilever is forced to bend down. And so if this works, then you've shown that there are external lateral forces here that are at the microscopic level. And so this is a little bit more detail on how the ball was corrugated. This tells the kind of gratings that were used. Dr. Thorsten Ludwig did thousands of runs, and indeed, when the blaze up, that is when the wedge angle pointed up, there was an up lateral force, and when the blaze was down, the grooves produced a down lateral force. So the experiment demonstrated that the Casimir wedge geometry produced atomic scale external lateral forces. So in order to go to the macroscopic level, we have to have a test article. And we start with a grating that I got from Thor Labs. And the original aluminum is removed using hydrochloric acid. An evaporator is used to recoat one side of the groove as shown. And so you see an evaporator filament, and that's producing aluminum atoms that move in a straight line. And so they coat one side of the groove. And that's combined with a mirror also from Thor Labs. And so this is what the test article looks like. There's the mirror, and the blaze angle is given to us by the manufacturer. There's a little arrow on the grating, so you can tell what direction the blaze angle is. And the grating is aluminized. In fact, you can see there's an aluminum coating on the grating, and that's because in the evaporator, the atoms were coming down at that angle. The grooves are perpendicular to the blaze direction, and so this is the scale that was used. It measures to 1/10 of a milligram. Next slide. Next slide. Oh, here we go. All right. So, what are the expected results? We used, you have to integrate the wedge equation over the area of the cavity. That's done here, and there's a lot of arithmetic. And basically, what we're interested in here, I did a lot of measurements of the normal force more than the lateral force. But you notice the weight difference is minus 87.8 milligrams. That's pretty big weight difference. And I have to talk about orientation. when I talk about these weighing experiments, because it turns out that orientation is important, and the expected results didn't predict any orientation factor. So here is one of our test articles, what I call mirror grading number 3, and I'd say the salient thing. Okay, there is the orientation problem here. There is this orientation problem, but if you do the average of these, it's asymmetric. There is a positive weight in one direction. Right, it's above 0. All right, so this is another grading, has a different pattern. I'm going to go through these kind of fast because they're sort of boring. But notice in all cases, there is an up and a down. They're both positive and negative measurements. There is this orientation thing. The orientation differs between different test articles, and there is this asymmetry. In this case, there's a positive net amount. This is lateral force. This here is, I oriented it 90 degrees counterclockwise. Let's see. This is with the doors open. This is in a Faraday cage. So I'm trying to get a handle on what's going on with the orientation. And this is number 4 again. I have to go back. These here have loops. All right, it says GM4 with loops, and the loops are the on the paper clamps. There are these things you press to open up the paper clamp. Okay, so you take those loops off, and it changes it. It lowers the amount that you get out here, the amount of force. I think I have an idea why. There's another no loops. This here is another. This is GM number 5, GM number 6. Now this here, it has the average weight difference is actually negative. And this is the weight difference is positive. This is GM number 6 again. GM number 7, weight difference is positive. This is number 8 with loops, and the forces are larger with loops than without loops. And again, the average weight difference is positive. Average weight difference is positive. Number 8 again. This is what? Normal forces. Oh, this is in a Faraday cage. Hello. 41, next slide. 42, okay. And this is in another Faraday cage. All right, now we get on to the float experiments. I think they're actually more interesting than the weight experiments. And this is my setup in the basement. It consists of a kitty litter box. I have a clear plexiglass top, and I have, well, I show the various parts. This is looking from a webcam down, and there's this floating tray, and you can put test articles there and a counterweight. There's a baffle there to keep things from moving, and it can be released and allow it to move, and that's that. Let's see. Now, at the bottom of the kitty litter thing, I have a pin that I have attached to the bottom. And associated with that is on the bottom of the tray, there are some washers that I glued on, so which will allow it'll allow the tray to rotate, but it won't allow it to translate. So here is a graph. This here is what's going on here. This is the angular position in degrees versus time in seconds. And the blue line is clockwise rotation, and the red line is counterclockwise rotation. All right. You can figure from this, you can figure out the radial velocity in degrees per second. And that's also versus time. Again, is red is clockwise, counterclockwise, and blue is clockwise. And then you can put those two together, and you get this interesting chart. It shows that all right, the blue is clockwise. So essentially, you can't see my cursor, too bad. Starts at the origin and goes to the right and just follows the blue curve around and ends. Oh, wait a second, no. Blue is clockwise, so it starts going to the left and goes around and ends on the right, and then continues and does a loop-de-loop and comes back to zero eventually and stops. And the counterclockwise, it also starts on the left, goes around. Maybe you can see hand motions better. It goes around, continues to the left, and does a little loop-de-loop and then comes back. All right, now this here is GM5. Again, you have position, radial position versus time, radial velocity versus time. And in this case, there's a very large counterclockwise component and a very small clockwise component. This is for GM number 5. Let's see, what's this here is GM3 and GM5 together. All right. And see that there are two bumps here. I think let's go right to this. All right, so on the left one here, this is the normal scale, and you can't even see the clockwise rotation. All you can see is the counterclockwise, and so it goes around. It does a little bump there, and then big bump, and then comes back. On the right is a log scale of this, and it essentially shows both test articles here, the effect of both test articles. And let's see, what is this? Oh, I wanted to get a feel for how these graphs change with configuration. So there are a number of configurations. I have counterclockwise, clockwise, and counterclockwise means that go grading, mirror. So, oh no, it's mirror grading. So if that is counterclockwise, mirror grading is counterclockwise, then that's the counterclockwise configuration. And then you have blaze up and blaze down. And so there's considerable difference here, including one block here with no clockwise or counterclockwise could be detected with the video. And this is for, the last one was for GM3. So this is the same thing for GM4. A lot of differences depending upon the configuration. This is GM5, same thing. Again, lots of differences depending upon the configuration. All right. Then I went on to unmodified gratings, and what are the expected results? Then you start with the basic wedge equation, and you integrate over the area of the cavities, and you have a different cavity here. In the test article, the cavity was determined by both the grating and the mirror. In here, the cavity is totally in the grating. Okay, and what are the expected results? All right, the weight difference for this is a positive 40.34 milligrams. So that's a fairly large amount. We notice we didn't get anywhere near this the expected when I was for the test articles, and so we'll see what happens with the unmodified gratings here. All right, so here's a weight difference graph for this particular grating, which I'm calling number 9, and it also has an orientation problem, call it. However, it is highly skewed in the negative direction. There's only that one little peak where it's positive. All right, so what about the float experiment for the unmodified grating? All right, so we got the angular position versus time, angular velocity versus time, and here's the plot of angle versus angular velocity, and in this case, the clockwise. Yeah, this blue is the clockwise. All right, so it's starting, and it goes to the right, and it comes around, and then stops. Wait a second. I don't know clockwise from counterclockwise here. Yeah, okay. Yeah, that's correct. That was correct. All right, so it goes clockwise, and the top one in red goes counterclockwise. The clockwise has a bigger loop than the counterclockwise. And here's a discussion of the results. Okay, why were the forces so much less than the expected for both the weighing and the float experiments? And the forces depend upon orientation for both weighing and float experiments. On the top, you see in the blue lines represent the calculated wedge forces, and I'm positiving another force, an edge force, and they're in red. All right, so there are wedge and edge forces for both the test article on top and the unmodified gratings on the bottom. All right, this edge force helps explain why the resulting forces are so much less than the expected. It also could explain why the forces are sometimes opposite to expected direction. Even explains why the unmodified grating forces are considerably less than the grating mirror test article forces. And the reason being, in the unmodified grating, the wedge and edge forces are directly opposed to each other. It doesn't explain the orientation problem. There was a suggestion that Earth's magnetism is somehow involved, and it may be. And while the grating mirror test articles were held together by these iron paper clamps, the unmodified gratings contain no ferrous materials. Right? The variability of results for the grating mirror test may be explained by minor differences in construction. And future investigations will use the unmodified gratings since they are simpler systems and are manufactured objects. Right. So next up, continue the float experiments using the unmodified gratings. With a sufficient number of them, will the tray go in full circle? If it does, it will show that in principle, the Casimir force is useful for propulsion. It will also be possible to calculate the power output, notice I say power output, of the quantum vacuum, or at least that part used by the test articles and unmodified gratings. And the reason being, if it goes around, there's a force that's overcoming friction, which can be determined, and force times velocity is a power. So what happens when the gratings are stimulated by ultrasound? I've done some preliminary experiments that show that ultrasound does have an effect on the grating forces. And what happens when they're stimulated by magnets? Ultimately, one would like to be able to make gratings with custom-shaped grooves. And that finishes the first one. All right, could we bring up the second one? I think I have time here. All right, here's the follow-up. This actually, I think, is more interesting. So all my next steps, I'm using the unmodified gratings, even though they don't produce as much force. They're simpler and they're manufactured objects. And what happens when they're stimulated by magnets and with sufficient number of gratings, will they go full circle? All right, so this is the unmodified gratings. All right, is it a simpler system? Okay, so what do I have here? These are my grating mirror combinations, and I've just chosen a particular configuration, counterclockwise up. So all of these are counterclockwise up, and they're all different. I mean, gosh. By the way, I've shown the orientation of north-south here. Now let's look at for the unmodified gratings, there's a lot more similarity. Right? In all cases, the counterclockwise is on the top and the clockwise is on the bottom, and the clockwise is bigger than the counterclockwise. So that's a big improvement over the grating mirror test articles. All right, so what happens when they're stimulated by magnets? Well, unfortunately, I had these iron poles holding up the webcam, and they caused the. At first I put the magnet. It's a samarium cobalt magnet, particularly strong, with an unmodified grating, and it just zipped around. It was crazy. But it came to rest at essentially the 90-degree position. Right? And my collaborator, Dr. Ludwig, says, you got these iron poles there. You ought to test it with the magnets alone. So I did. And They also zipped around, but they came to rest at the 270 degree position. So there's definitely a difference between the magnets with with the gratings and without the grating. But it needs, essentially, my apparatus needs to be run. You need to remove all the magnetic material here. So I'm in the process of that. Now this here has no magnets, and the question is, with a sufficient number of gratings, will the tray go full circle? So my first attempt at this shows a sort of a regular. It looks like all the others. You know, there is this is a counterclockwise in red, and the clockwise in blue, and the velocity here, and it looks like all the other. At first glance, it doesn't look very promising to go full circle. However, you'll note that after I stopped recording, it went further. And I have noted here, eventually clockwise stops at 165. However, it just slowed down there. It actually kept going. All right? And it went around 3 times. The first time I didn't document it, but the other 2 times I documented it. And so these are the traces of the clockwise 1 and clockwise rotation 2. And they start at actually 139 degrees. And you see it goes full circle. It ends up at minus 220, well, actually 221, which is 139 degrees again. So they both went full circle. So it has really horrible velocity characteristics here. But for the blue one, all of the readings are below 0. All right, so it is they're all going clockwise. For the red, there's a brief excursion here. It goes counterclockwise and then reverts to going clockwise again and completes the full circle. And the data was acquired by eyeballing at long and uneven intervals, which is another reason why the plot is so crazy. It's too slow for tracker. So plotting these, you see, they both go full circle. They both go around the center. And doing this in log mode, the log plot, it's jagged, yes, it's slow. Rotation 1 was about 16 hours. Rotation 2 was more than 21 hours. But it went full circle. I'm missing something here. Oh, I forgot to note the one on the top. This is a non-rotating neutral object. So, yeah, if you put a neutral object in the tray, it doesn't rotate. Right, so that's important. All right, it's not a result of the Coriolis effect. It's rotating clockwise. Coriolis effect in the northern hemisphere would be counterclockwise. And let's see, the full rotation means that in principle, energy can be extracted from the vacuum. It was a surprise that only 3 gratings could go full circle. I had anticipated that it would take 12 or more. And also interesting here, the clockwise rotation results from an edge force, not a wedge force, right? All my calculations were for wedge forces, but it turns out it's an edge force that is moving this. It's even bigger than the wedge force. Can't explain why clockwise rotation suddenly goes counterclockwise and then just as suddenly resumes going clockwise. It was assumed that there was a conservative, non-conservative dichotomy. And my question is the real dichotomy here wedge wedge force versus edge force. And I still don't really know the reason behind the orientation problem, although it is suggestive that the traces for the unmodified gratings seem to orient along the north-south axis. Let me just go back to that if I can. Come on. I'm still on slide 10. I'm not moving. 8, 7. Okay. All right, this is the south orientation here between the clockwise and the counterclockwise. I mean, you have to squint to see it, but it may be there. So, and that's the end. Thank you very much.